There is an analogy between fluid flow and heat transfer, convective heat transfer, that is used to evaluate the convective heat transfer coefficient by measuring frictional drag. So this analogy, heat transfer fluid flow analogy, or Colburn analogy, is used to determine remember, for the wall shear stress, tau S is mu du over dy at y equal to 0. And then we're defining this friction or drag coefficient, Cf of x, which is tau S over 1 over 2 density u infinity square. Now, through the solution of flow equations inside the boundary layer, we can find out this drag coefficient. Cf of x is 0.332 Reynolds of x to the power -1 over 2, and this is Laplace's solution for laminar boundary layer. And what we will see in the upcoming lecture, we are gonna have a similar expression for the Nusselt number, which will be 332 Prandtl to the power of 1/3 Reynolds of x to the power of half, and that's Laplace's for energy equation. If we divide both sides, so if we divide Reynolds, so what we are going to get is number of x divided by Prandtl Reynolds of x, 0.332 Prandtl 1/3 Reynolds half. The right hand side is going to be 0.332 Reynolds of x to the power of half. The left hand side Nusselt number is local heat transfer coefficient, x divided by k. Prandtl number is mu c divided by k, and Reynolds is rho u infinity x divided by mu. So these x are canceling out, k, mu. What we are ended up is hx over rho c u infinity, h of x, so the local heat transfer coefficient. This is on the left hand side, which is equal to the right hand side, and this part is cfx divided by 2. So it's going to be CFX divided by 2 times parental to the power of minus 2/3. Now we define a new dimensionless number and we call it Stanton number as a ST of X. So in general, Stanton number is H over rho C U infinity, which is Nusselt over Prandtl Reynolds. Now, if I use this definition of Stanton number, then this equation, actually this part, essentially would be Stanton number X until to the power of 2/3 is going to be 1 over 2 CFX, which is the drag coefficient here. And this is valid until less than 50, greater than 0.6. Now, the significance of this, this is the analogy between the heat transfer. So the Stanton number and the fluid flow through the drag coefficient CFX. Now, this is what we call, or was introduced by Colburn as a Colburn analogy. And which applies, can be applied in both and turbulent flow over plate. And the use of that here is that if we have this drag coefficient, we can evaluate this Stanton number, and from there we can evaluate the local heat transfer coefficient.